Welcome back, and welcome back to your Chem 1802-1806 lab. I'm Dr. Alaban. Dr. Hathcock is back there running the computer, which she tried to wave. I'm not sure if you guys saw her, but she's trying to wave. But today, we are going to be talking about the fundamentals of calorimetry. Now, this is a little bit of a tough lab. We did kind of take some background knowledge into this lab and rework it just a little bit to help make it easier for you guys. So we're going to try and make this lab as easy as we can for you, but just a heads up, this is still going to be somewhat of a tough lab. Okay, yeah, in all my papers here, I have hidden up the materials list for myself. Okay, all right, so for this lab, you are going to need styrofoam cups. You should have 3 of them. And as I was going through the box for the calorimeter, first box I opened, 1 or 2 cups had a hole in them. Okay. I opened up a second box from another kit that I had and the same issue. So check your styrofoam cups. Make sure the bottom of the cups are intact. If they are not, then Walmart, Dillon's, your local grocery store will have some styrofoam cups for you to use. So you will need styrofoam cups. You will also need calcium chloride. You will need ammonium chloride. You will need a thermometer. I'm using a bigger thermometer because the one that was shipped to us is still broken, so I'm using one that I have available to me, but you should have your thermometers with you. You need some weigh boats because you're going to need to measure out some solids. You need your 50 milliliter graduated cylinder. You need a spoon. You need a balance. And you need the 250 milliliter beaker. So you don't need a whole lot of stuff for this lab, but that is the supplies that you will need. All right, so what we're looking at in this lab is thermodynamics. So we're looking at the energy transfer, or the study of energy changes that occur from physical and chemical changes. And so to study that energy change, we are going to be looking at a specific area called calorimetry. Okay? And so what we're going to do with calorimetry is measure the amount of heat exchange. One thing to keep in mind on this is that heat will always flow from the hot or warm object to the cool object, never the other way around. So when we're looking at sign changes, the hot substance should always have energy flowing from that. So the energy value will always be a negative sign when we are doing calculations. Okay? That negative sign is just there to show you the direction of the heat flow. And so if something is going to lose heat, reaction or substance is losing heat, that is exothermic because heat is, or energy is exiting that system. An endothermic value means that that substance or that system is gaining energy, so you should have a positive Q. Now, energy is always going to have a positive value, but in these calculations, that negative and positive sign just simply shows you the direction of the flow that it is going. Okay. Yeah. What we're going to start off with for this experiment, okay, is determining the heat capacity of the calorimeter. Okay, so that's going to be what we do for the first part of this. And then activities 2 and 3, we are going to be determining the enthalpy or molar enthalpy for a reaction using calcium chloride and ammonium chloride. Okay. Yeah, all of these reactions.
Sorry.
Well, we all know Dr. Hathcock is alive back there. But so we know all these reactions are going to be done at constant pressure and constant volume. And because these reactions are going to be done at constant pressure, delta Q is going to be equal to the change in enthalpy. And if we want to find the molar enthalpy, we'll know the moles of our substance, and we just have to take the Q divided by the mole. But finding the molar enthalpy is going to be activities 2 and 3. All right. Yeah, there are a couple of terminologies that we do need to go over before we start getting into what is back here on this screen. Endothermic and exothermic, I've explained to you. Endothermic is looking at a substance or a reaction absorbing or gaining heat. Okay. Exothermic is where heat is released.
Give your examples.
Okay. So if you think about a hot pack, you're in the middle of winter. You're standing outside at a football game. My hands are freezing if I forgot my gloves. But somebody next to me, hopefully, maybe my dad was thinking about me, or maybe you happen to find a friend who took pity on you. They have a heat pack or a hot pack. And you activate it and you stick it on your hand and you put it in between your hands. What happens? You feel the heat coming off. Your hands are getting warmer. Your hands are absorbing that heat. Because your hands are absorbing that heat, that means whatever's going on in that hot pack, that reaction has to be exothermic. Because that reaction is giving off heat, but your hands are absorbing it. Okay. Think about an ice pack or a cold pack. If you activate that, you put it on your leg or your arm, wherever you've gotten injured, what do you feel? If you lift that cold pack off of your leg or your arm, that part of your skin is cold. Because that cold pack is drawing energy from your skin and into that cold pack. So given time, that cold pack is going to get warmer and warmer because it's drawing energy from your leg. So because that cold pack is drawing energy into that reaction or that system, that is going to be endothermic. So endothermic always is going to draw energy into it. Exothermic is always going to be releasing energy. And a lot of times another easy way to think about this is why do we add acid to water? The one that I see the biggest change on is when we add sulfuric acid to water. So if I'm adding sulfuric acid to water, this graduated cylinder gets incredibly hot. Okay? So it gets very, very, very hot. I have to walk away from it and let it cool. That's because there's an exothermic process going on there. That system, that mixing, that solution making is giving off energy to the surroundings. I'm feeling that energy coming off in the form of heat. Now, if it wasn't endothermic, I would feel that graduated cylinder getting cold. Yeah. Another important value that we're going to see is called specific heat. Okay. Specific heat tells us how much energy is required to heat 1 gram of substance and have its temperature increase by 1 degree Celsius. So how much energy is required for 1 gram of substance to have a temperature change by 1 degree Celsius? Now, every substance has its own specific heat value. Okay. You're not required to memorize all of them because there are so many substances. Okay. So a lot of those specific heat values can be determined from tables, reference books, or internet. One that you should be familiar with is water. Water has a really high specific heat, so it's going to take 4.18 joules of energy to increase 1 gram of that water and have its temperature increased by 1 degree Celsius. So to increase 1 gram of water's temperature by 1 degree Celsius, it will take 4.184 joules worth of energy. So, what we're wanting to calculate for the first part of this is to be able to determine in activity 1 what the specific heat of that calorimeter is. So in your labs, ignore page 4, equation 1, 2, and 3. We're going to go through and show you some different calculations. Okay, you'll end up at the same point, but hopefully this makes a little more sense than what you see in the handout. So to find Q, okay, it's going to be mass times the specific heat of a substance times the change in temperature. Delta T can be a negative value if the temperature drops or goes below that initial temperature. Delta T is final temperature minus initial. So you can have a negative value here. Mass and specific heat have to be positive values. So if you have a negative sign here, then you will end up with a negative Q, meaning that that system has lost energy. If delta T is positive, then Q will be positive. Now, for your reaction, or for part 1, we are going to be adding hot water to cold water. So this part right here is going to be looking at how much energy, if I'm thinking of this right, because this is making sure I'm getting my equations here. So hot water should be losing energy. So therefore, this part of the equation, just that part right there, should be negative because final temperature, so looking at hot water, final temperature should be lower than the initial because temperature has dropped. Okay. That negative sign right there is going to make that positive so that I can determine how much heat or how much energy that cold water has gained. Okay. Now I know that's a little confusing. Okay. The idea behind this is if something loses energy, something has to gain it. So even if I just got rid of that part right there, just to maybe make this a little easier to follow. This is how you have to calculate Q. Mass times specific heat times change in temperature. Okay. Again, this is the only part that can be negative. So you have grams, that's your unit for mass. Joules per gram, degrees Celsius, those are the units for specific heat. Degrees Celsius, that is going to be your unit for change in temperature. So grams and grams, these two units are going to cancel. Degrees Celsius and degrees Celsius are going to cancel as well. Okay. So that's going to leave joules to carry through. And let's just get rid of that right there so I hopefully don't lose you anymore. Okay. Now, if something loses heat, where did that heat go? Or if something gains heat, where did that heat come from? Okay. So these negative and positive signs here show the direction of that heat flow. If water's temperature increases, that means it's gaining that heat, it's gaining energy. But where did it come from? It had to come from the reaction. So the reaction is losing that heat. So if the reaction lost 1 joule worth of heat or 1 joule worth of energy, that water had to gain that same amount. So whatever that reaction loses, the water has to gain that same amount.
Just to pipe in real quick, it's called the law of conservation of energy.
Yep.
What goes in, theoretically, must come out. Energy is neither created nor destroyed.
So yeah, if something's gaining heat or energy, where did it go? Or where did it come from? It's not being created, it's not disappearing, it's just going to somewhere else. And so, but we just happen to know where they go.
It's being transferred, so to speak.
Okay. All right. So in this experiment for activity 1, you have hot water and you have cold water. So if I want to determine the heat, the energy gained or lost by water, I need to know mass. I need to know the heat, the specific heat of water, which is 4.184 joules per gram degree Celsius. Okay. Refer back to page 4 if you didn't catch that, or if you need to refer back to it multiple times. Okay. Times the change in temperature. Okay. So temperature change is final minus initial. Okay. Again, energy from a hot substance is always going to flow to energy is always going to add to the cool substance. Okay, so whatever's cooler in temperature, it's going to have an energy increase. So if that difference right here is positive, that means this Q value is going to be positive. Okay, so there's going to be an energy increase for here. If your final temperature was lower than your initial, then this would be negative. Okay. So whatever sign this is positive or negative, it's coming from here. Okay. So if final temperature is greater than the initial temperature, then that change right there will be positive, and that's going to make for a positive Q. Okay. So we should see this for your cool tap water. Yeah. Another information that you want to be careful of is temperature and heat are not the same thing. Temperature is a measurement. We have thermometers to measure that, and we have a scale for that. Temperature is not dependent upon the mass. The amount of heat is dependent upon the mass. So if I change the mass of that substance, so if I change the mass of water, that amount of heat lost or gained is going to change. Not the temperature, but it's just going to be the heat. So heat is looking at an exchange. Your hot, your warmer substance is going to give energy, or it's going to give heat away. So again, temperature is just a measurement. Energy is looking at, or heat is looking at an energy exchange. But this is also dependent upon mass, whereas temperature is not. All right. Now, another part that we have to consider for this is you're adding hot water to cool tap water. So hot water should be giving energy to the cool tap water, but it's also giving energy to the calorimeter, which is your styrofoam cups. So we have to determine how much heat that calorimeter is gaining. So again, we're going to use this energy equation, mass times the specific heat times your change in temperature. But for the calorimeter, the mass and its specific heat are going to remain constant. Okay. So if these two are multiplied together, that's going to come and be converted to the specific heat of the calorimeter, or heat capacity of calorimeter. Okay. So this part right here, the heat capacity of the calorimeter, is just from multiplying these two values right here because they remain constant. Okay. So heat capacity of the calorimeter times your change in temperature. Now again, if final temperature is greater than initial temperature, then Q will be positive here. And for activity 1, this equation for cool tap water and your calorimeter should both be positive. So both of these should be a positive Q value when you calculate them. All right, so the idea is for part 1 that we want to determine what that value is. So we know what Q of calorimeter was, and maybe I should have not done that. So this is now your Q of this is the Q of calorimeter. We're going to have the heat capacity of the calorimeter times our temperature change. Okay. So heat capacity of calorimeter times our temperature change. That's what that part right there represents. Okay. Q of water cool. Okay. So the heat of the cool tap water. These two both should be positive values when you do your calculations. That means both of these are gaining energy. They're gaining heat. But where did that heat come from? It had to have come from the hot water. So the total amount of energy that the hot water lost is the total amount of energy that was gained by the sum of the cool tap water and your calorimeter. So once I get this part here, it just becomes an algebraic problem. Q of calorimeter, again, is the heat capacity of the calorimeter times delta T. Cool tap water, okay, so that part right there is the total amount of heat gained, equals the Q, or the heat of your hot water. To find the heat capacity of the calorimeter, I'm just going to start doing some subtractions and dividing. So I want to subtract the heat of cool water over to the other side. Okay, so I'll subtract on both sides. So here, the cool tap water is going to be subtracted over here. So now I have the heat of hot water minus the heat of cool water. So that just now leaves the heat capacity of delta T, or heat capacity of calorimeter times the change in temperature. And if I divide the change in temperature on both sides, that just leaves me the heat capacity of the calorimeter. And we have just now solved for equation 3. Different way, hopefully, fingers crossed, you understood how we got here, because this part right here is just another form of what we're going to do here, but hopefully in simpler understanding. And again, fingers crossed that you followed what I just said. Okay. So, if you guys have questions, I hope Kristen's going to forgive me for this. Email us, ask us for help. If I don't get questions, I know something's wrong. Either I did a really good job of explaining it, or you guys just don't know what to ask. But please, again, just ask us. Okay. And as you start to do some of these experiments, hopefully it'll make it a little bit easier for you to follow. All right, so I'm going to try and kind of show you what we've got here. Okay. So first part of this again is just determining the heat capacity of the calorimeter. Okay. All right. So since I have lost a few styrofoam cups, I had to kind of go get a bigger styrofoam cup. So there's actually 2 cups inside. You're going to put 50 inside this inner cup. Okay. All right. So again, 2 cups inside here. I just have, I lost so many cups. Stick your styrofoam cups inside the beaker for support so they don't fall over. Measure your temperature of your cool water, and you need the hot water to be 75, 80 degrees. If it's not, if you don't have it at 75, 80 degrees, add it to a microwave for short bursts. Be careful not to melt anything. We are not going to be responsible for any replacement of microwaves or any other heating devices. Okay. So I've got my thermometer in cold water, so it is equilibrating. Oh, we've let ours get a little too warm, but hey, we're going with it. You guys use 75, 80 degrees. Follow the instructions on this part. Okay. So I'm going to go ahead and mark this at about 92.
Don't do what the instructors do.
We're at 92. So, again, while we were talking, we kind of forgot about this. And, okay. 50 milliliters of hot, and
don't burn yourself.
Yeah, that's kind of warm. Okay, and we're going to add this to our cold water, and then we're going to measure the temperature change at 1 minute intervals until we complete the box on the left on page 8. So I'm going to say stay tuned, and we will be right back after our commercial break. All right, guys. One thing I did forget to mention in the materials list is you do need a timer. As I'm sure you've probably noticed, you need something that's just going to allow you to keep time so you can measure at these 1 minute intervals. Okay. So it's been 10 minutes later. I've measured the temperature changes for my particular experiment. Yours should be a little bit different since you actually followed the instructions and used 75 to 80 degree temperatures. Okay. You're going to use this information on this side of the data table to create an Excel graph, okay, or what's known as a calibration curve. So you should have something that looks like this. Time goes on the x-axis, temperature goes on the y-axis. There are links to how to use Excel if you're not familiar with it, provided within the instructions of this particular lab assignment. So your instructor has given you that link if you are unfamiliar. Okay. Once you build your calibration curve, you will get an equation, and you can use that equation to determine what y is. And remember, for this part here, we need our initial time. So your x will be set to 0, and then we will determine what y is. And that temperature is going to be right here on that line. So temperature at time 0 from calibration graph. So we need the initial temperature. Once you have that, you're going to go through the rest of these calculations, and you will determine the heat capacity for calorimeter. Pay attention to the calculations because it tells you exactly what you are going to be solving for. So here you're solving for a Q of hot water, and once you determine that value here, you notice that Q of hot water is down here. So what you've got for a value here, you're going to plug in here. Okay? So some of these equations that you use up here will be needed down here. So pay attention to those units and what you're solving for. Okay, I'm going to set up and show you real briefly how to do activity 2. Activity 3 is the exact same experiment, just with ammonium chloride instead of calcium chloride. So I'm going to go ahead and just set this part off to the side here. And you need 100 milliliters of water into your calorimeter. We still need to determine the initial temperature. Okay. I'm just going to let that. While you've got your 100 milliliters set in that calorimeter and you're letting that temperature equilibrate, go ahead and weigh out 5 grams of your calcium chloride. Okay. And you need to know exact mass, so what your balance says, make sure that you record that. So I've got 100 milliliters of water here. I've got 5.06 grams of calcium chloride here. So my initial temperature of water, 20 degrees. So that's going to be the initial temperature. I'm going to go ahead and mark that down in data table 2. And one thing that you don't want to do is let calcium chloride sit out for too long. And with all the introduction and activity 1 experiment, I let mine sit out just a little too long. So yours is going to be a little bit easier to pour. But I've got my 5 grams. I'm going to go ahead and add this to the calorimeter. And yours is going to be much easier to deal with because it hasn't sit as long as mine has. All right, you're going to stir this so that it dissolves, and you are going to keep stirring until the temperature stops rising. This may take a few minutes to do. All right, so I've been stirring for a few minutes, and I've got my temperature for this 5 gram sample to go to 26, and since I'm not seeing any that temperature rise any farther, this part of the experiment is done. Okay, so I'm going to go ahead and mark that final temperature of 26. I will discard this solution down the drain. Prepare another sample of calcium chloride, but using 10 grams and doing the exact same experiment again. And then I'll discard that solution down the drain and perform the experiment again with 15 grams of calcium chloride. Okay. And then I'm going to follow again very carefully, looking at what this table is asking me for. I'm going to solve all of these calculations. Okay. And I'm going to then get the enthalpy of solution, enthalpy for mole of solution. Okay. So you know how much of each one of these samples you've used. You know how much calcium chloride was in that cup. Okay. So therefore I can determine what the average enthalpy per mole is. Right. Once you've completed the calculations for calcium chloride, you're going to do the exact same experiment again using ammonium chloride. Okay, so I'm going to spare you that part of it since we should be familiar with that. You just make sure you know the exact mass of ammonium chloride, your mass of water, your final and initial temperature changes. Go through the table again. And then you're going to use this information here in this table to help you answer the questions and solve for that problem in activity 4. Okay? And that is, this lab in a nutshell. Hopefully you guys are following what was going on, and I wish you the best of luck with it. And if you need us, we are just an email away.